This is question number 4 from the 2005 exam. It says that breakfast cereal of a certain type has vouchers for free video rentals. The company says we can find the voucher in 20% of the boxes, but a group of students who eats a lot of this cereal says maybe it's less than that. They purchased 65 boxes and found 11 vouchers in the 65 boxes. Suppose it's reasonable to assume these 65 boxes are a random sample. Based on what we have from this sample, is there evidence to support the belief that the truth is less than 0.2? Provide statistical evidence to support your answer. I personally think that this sentence right here is unnecessary because it's a free response question. You got to do that if you want to get any credit, because you've got to do that if you want to have any credibility. This question will be divided essentially into 4 parts. We've got the part where we set up the problem, the part where we check the conditions for the problem, the part where we do the mathematical work for the problem, and the part where we do our conclusion in context. So, first of all, first part, the null hypothesis is that P is 0.2 versus the alternative, it's something less than 0.2, where not 0.2, where P, holy moly, the true proportion of boxes with a voucher. Next, we want to check the conditions for the test, and it says we have a random sample, so thankfully my sample is random. That's this part here, random sample. Secondly, we need to make sure that the 10% rule is met so that the boxes are independent. Certainly, the 10% rule is met because more than 10 times 65 boxes will be made. And finally, we need to check and see if our sample size is large enough. So I want to make sure that I have enough successes and failures to make this work. Since this is a hypothesis test, I'll check it this way. Since NP is greater than 10 and n times 1 minus p is greater than 10, I am safe to assume approximate normality. Now I need to check and make sure this is right. I'm pretty sure it is, because 65 times 0.2, is that greater than 10? Yeah, that's 13. That's greater than 10. And is 65 times 0.8 also greater than 10? Yeah, that's going to be greater than 10 as well. That's going to be 52 is going to be greater than 10. So I'm good in both cases right there. And then, therefore, I will perform a one sample Z procedure for proportions. Third part of this says that we want to actually do the math. So the math comes in looking like this. Z, we got a little normal curve going over here, and Z is going to be P hat minus P over the square root of P times 1 minus P over N. So P hat was 11 out of 65. So this is 11 out of 65 minus 0.2 divided by the square root of 0.2, 1 minus 0.2 over 65. Now I probably don't want to do that the long way, so I can pull out my calculator and I'm going to go stat test, one prop z test. My p hat is, or sorry, p naught is 0.2, and this is 11 out of 65 boxes, and I want to know if that's actually less than 0.2. So I calculate it, chicka chicka whir whir. Here's what I get. This z is negative 0.62, which means this area is my p-value, and my p-value here is 0.267. .2676. And now I want to talk about the conclusion and put that in context. Now here's my p-value. I'd compare that to an alpha level. I don't recall an alpha level in the problem, but nevertheless, this number is bigger than any reasonable alpha level that I can recall ever using. So since p equals 0.2676 is larger than any reasonable alpha level, I will fail to reject HO in favor of HA. Now I'm going to put it in context for you. That is, I do not have sufficient evidence to reject the manufacturer's claim that 20% of the boxes have vouchers. There is a good answer. I've included all four parts, and I like the way this looks. So now I want to go through the rubric and see what sort of grading system this would actually get me. So they divided the answer up into four parts, similar to the way I did when I worked it. They want you to have a correct pair of hypotheses, identify the test and check the conditions, use correct mechanics and math, and then give me a conclusion in context. And so let's look at how the grading would work. For the first part, it says each part is either going to be an E for essentially correct or an I for incorrect. It's essentially correct if you state a correct pair of hypotheses. In other words, if you didn't do that, you got an incorrect. Note this is a good note here. Since the proportion's already defined, you don't have to define it. But if you used a two-sided test, you got it wrong because they wanted to know if it could be less than. So an E or an I on part A, write that out there in the margin. Part B, essentially correct if you identify the correct test by name or by formula and check the appropriate conditions. So the appropriate conditions were the things that we talked about when we did it, namely that 52 and 13 are both bigger than 10, that the 10% rule is met because they can make more than 650 boxes, and that I have a random sample. Now, when it talks about the correct test identified by name or by formula, I did the name when I did my conditions, but you'll recall I did the formula down here a little lower. It actually doesn't matter exactly where that is because they can see that I've got it one sample Z procedure for proportions as well as the formula itself down here. So I'm in good shape for that personally on getting an E. Remember it said it was an E or an I. So apparently on this one, if they didn't do all this, they got an I. Part C is essentially correct if no more than one of these errors occurs. So one error would be okay. More than that, not so good. Undefined non-standard notation. You got a z of negative 0.62, but no setup. You got a z of negative 0.67 because you used p hat in the bottom. In other words, down here where I used 0.2, if you used p hat, you're going to get the wrong z-score. You'll get a 0.67 instead of a 0.62, and therefore wrong p-value. And if you did some minor arithmetic error. So if you only did one of these mistakes, but you got the rest of it right, you get essentially correct. An incorrect if you used a two-sided p-value with a one-sided hypothesis test, or you got some unsupported z-value with nothing, no setup, or you've got the right answer, but somehow miraculously the wrong formula. One mistake, okay. Multiple mistakes, incomplete. Probably didn't do it with the exact binomial function, but if you did, they accepted that as fully complete and correct. That's the way it would be if you worked it as a binomial problem. And here's a couple of other things that you could see that I don't necessarily cover in my class. The continuity correction. And we typically don't do it with a rejection region in my class, but you could. If you use the confidence level approach, then you could figure out the interval and decide whether 0.2 is in there, and it is, but you have to go with a 90% interval. Part D, essentially correct if you do this stuff. You list the p-value with linkage implied. So I said there was no alpha, but that's how you would find the alpha because it was really big, or the p-value was really big comparatively. If part C is wrong, but you're consistent, you can still get an essentially correct. But if you say you want to accept the null, then that's incorrect. So we can't conclude the proportion is really 20%. We simply don't have enough evidence to reject that idea. Finally, to score it, they get 1 point for each E, a half a point for each P. Except on this problem, you couldn't actually get a P. So you get 1 point for each thing you got right. And there's your score. Write that number over in the margin.